So we've derived an explicit method for the diffusion equation called the forward time centered space method. Then we did the von Neumann stability analysis on that method and showed you that you're limited by the size of your time step. If you take a time step too large, then the method will become unstable. You can avoid instability in a numerical method. Instead of using an explicit method, you use an implicit method. So I'd like to show you what an implicit method looks like for the diffusion equation and what the von Neumann stability analysis would also look like. So here is our grid. So we can do our forward time stepping. So we can use these grid points to do time stepping. But then remember, for the forward time centered space, we calculated the second derivative at the time step L. That's why it became an explicit method, because we're trying to find the value of u at L plus 1. For the implicit method, instead of calculating the second derivative at time step t sub L, we calculated at the forward time step at t sub L plus 1. So we calculate the second derivative using these grid points. Okay? That's a little bit strange, but perfectly fine. Calculate the second derivative at the previous time step, or calculate the second derivative at the current time step. If you do that and you write down the scheme, what you'll get is u sub j at L plus 1 is equal to u sub j at time step L plus delta t d divided by delta x squared times then the second derivative would be u sub j plus 1 minus 2 u sub j plus u sub j minus 1. But here we're evaluating at the L plus 1 time step. So this is at L plus 1, L plus 1, and L plus 1. That's our scheme. It's called implicit because you can't just plug in the value of u at L to get the value of u at L plus 1. What you need to do then is to put the L plus 1 on the left, the L on the right, and then you end up with a matrix equation. So for each time step, you actually have to solve a matrix equation. More sophisticated, but still possible to do. OK, now what I want to show you for this method, that this method is going to be unconditionally stable. So we're going to do, again, the von Neumann stability analysis. So we're going to try our mode. So we're going to try u sub j L equals psi to the L times e to the I k j delta x. That's our single Fourier mode. Substitute in. It's the same algebra as the last video, so I don't need to repeat it. You substitute in. You divide through by this factor, psi to the L times e to the I k j delta x. The difference here is that you'll end up with an extra factor of psi on the right-hand side. So what you'll end up with is a psi equal to 1 plus 2 delta t d over delta x squared times psi. You have an extra factor of psi there, times cosine k delta x minus 1. Okay? So the difference between the explicit method and the implicit method is exactly this factor of psi. So we can take this equation and solve for psi. What we end up with is psi, putting this on the left-hand side, factor out psi, and then divide. You end up with psi is equal to 1 divided by 1 plus 2 delta t d over delta x squared times 1 minus cosine k delta x. Okay? Let's look at this value of psi. So we have to look at all the wave numbers k, right? Can psi have a magnitude larger than 1 for any wave number k? If it can, then the scheme can be unstable. But we look at cosine k delta x. So that can be 1, at which point 1 minus 1 is 0, so psi is 1. Then when cosine k delta x becomes smaller than 1, then this one will become positive, right? So we have 1 plus a positive number in the denominator. That will be smaller than 1. So 1 divided by 1 plus a positive number is less than 1. Down to cosine k delta x equals minus 1. So this becomes 2. And then we end up actually with the largest positive number here in the denominator. So we see that this psi then has a maximum value of 1, which is the marginal stability case, but is always between 0 and 1. So psi is never larger than 1 in magnitude. So the scheme is unconditionally stable. Unconditionally stable. Okay? Because this value of psi never gets a value of in magnitude larger than 1. Okay. So let me summarize. We changed from an explicit method where the spatial derivatives took place at time L to an implicit method where the spatial derivatives take place at time L plus 1. We have our implicit scheme. We try the von Neumann stability analysis on the implicit scheme. That introduces an extra factor of psi that wasn't there before. So then we have to solve for psi, and we show that psi never has magnitude larger than 1. So this scheme, no matter what time step you take, will be unconditionally stable. That's a better situation to be in than to be in a scheme that can blow up on you. It turns out that if we combine both the implicit scheme and the explicit scheme, we get a very nice scheme that's called the Crank-Nicholson method, and we'll see that in the next video. I'm Jeff Chasnov. Thanks for watching. See you in the next video.